And Tomáš will give his last talk before we have a panel discussion of all 4 speakers. So Tomáš, take your time and the floor.
Okay, thank you for the word back. And similarly as Ondra was talking, I was thinking about what project to show, some project with impact. So today we also wanted to show some project that can have a big impact. It doesn't have yet, but I would like to talk about a sensor that is actually able to tell you if your mango or avocado or your apple is ripe enough to eat, or you can store it in the fridge or in your basement for a month or for 2 months or for 3 days. So that's the project. So what is the motivation? In the supply chain, some research says that even 50% of all fruit and vegetable can get wasted. Some get wasted because of the poor methods of the quality control. So usually you use some destructive methods. So that means that you will take a pack of mangoes, you will cut one mango, you will measure if it's or you will look at it if it's brown, or what is the firmness of it. If it doesn't comply with the quality, you throw the full bucket or the full box. So 10% of all the fruit is disposed during those checks, and 80% of that is actually healthy. And that's something what we wanted to fight. So you have on the field, you actually would like to know how ripe is it to even harvest it. So that's a little bit different problem, but with our partner, we are tackling it as well. But mainly, we are focusing on the checkpoints that are before or after the distribution. So you have there when is it harvested at the field, then at the arrival to the distribution area, it's tested. Then it's actually some artificial ripening is going there, and then before it's distributed to the shops, again you are doing some checks, typically on the sorting lines. So goal of our project was to develop a sensor, so ideally contactless microwave sensor that can tell us the information about what is the inner state of the fruit. To develop the software, so we knew that there doesn't exist sensor that can measure it directly. So that was the place for AI to actually be able to derive from the measurements what is the inner state of the fruit, and of course prove the performance on the sorting line. So we didn't do it alone. We did it in a consortium. We had a company that actually developed the sensor, because Datamole doesn't make hardware itself, and then of course we don't have any sorting line, so we have a partner that actually has sorting lines. So how that solution look like? This is very much in a nutshell, and I will show you. I will show some details. So you can imagine it. You have sorting line. You have the fruit from the farm. You have their sensor that is added to that sorting line. There is embedded PC that collects all the data, connects to the cloud, where we have models about different type of fruits, because there are different models for apples, different model for mangoes, different model for avocados, or different models for tomatoes, and you get a response about okay, how ripe it is, and then you can sort it in the right box to be either consumed immediately, or can be stored, or can be given with some flags. So as I said, it's starting with the sensor. So the main method today is a really manual cutting. So you cut it, you measure it with a refractometer or with other devices to find out what is the status of the fruit. You destroy that fruit at that moment. Then you have non-destructive methods, and very common is optical measurement. The problem is with optical measurement is that it penetrates the fruit only into approximately 2 millimeters of the fruit, so you don't see what is actually inside. And that was the first step that for the success of the project was that the sensor, the microwave sensor that developed our partner, is a sensor that can actually penetrate the fruit into 2 centimeters of the depth. So we can see what is in 2 centimeters under the skin of the fruit without actually cutting it or anyhow damaging it. And yeah, when Jakub was talking about hiring people to go with the phones, so yeah, measuring the data, that's real pain. So a lot of apples, a lot of mangoes. You really have to measure each individual fruit, each individual apple, each individual mango, and because we needed a reference, we also had to do all the cutting with all the fruits that was there. Thanks God, main part of this work was done with our partner that is in the Netherlands, but we know that they don't buy apples in the stores anymore. They don't like that. So what we are actually predicting, we want to predict the ripeness and predict the shelf life, and you need some proxy to that because definition of ripeness is usually reflected in something. So we are reflected in firmness. So how firm is it? We reflect it in how much sugar can be there, how much dry matter is there, or how much breaks. And for each fruit, you usually have some stages into which you want to classify them. So it's a kind of classification problem. So the measured data looks like this graph. So this is what you get from the sensor. So it's a microwave sensor that is from 0.25 to 40 gigahertz. So we in total collected data from almost 2,000 mangoes and from 4,000 apples. So you can imagine the scale of cutting it. And from this data, we need to get how ripe the fruit is. So we have 2 models. One is for the ripeness of fruit, and another one is for the shelf life. So the problem that you have there is that you have very small data set, even though it looks big. Yeah, within data science knows now that's not a big data set. And you need to capture quite complex patterns, but ideally with the simple features. So deep neural networks, slow to train, very data hungry, they are complex to tune. So how to approach that? So how we approached it is that we transfer actually the data by large number of convolutional kernels. So the method is called Rocket. And then actually you use some model that will regularize very well, that is very simple. So simple linear classifier. So this is how you can imagine it. You convert this data into some very simplistic features, and the features you then fit with some simple linear model. So worked pretty well. Later on, we found out that PLS works well as well. but when you have a lot of features, the number of features is way larger than actually number of your data points. You need to go for models that are very simple, very robust in regularization. So that was for the state of the fruit, and then for the shelf life. So there the problem was even bigger because we had pretty much 3 to 4 measurements throughout the lifetime of the fruit. So you measure it 1 week, another week, another week, another week, and then actually it's already end of life. So you have 3-4 measurements, so even more or even less data that are available. So many features, again, highly correlated. The dataset is small in comparison to the number of variables. So we need, again, some robust, highly regularized model. We cannot even use Rocket because we have even less data than before. So sometimes the big AI, it's in a very simple model. So a rich regression was actually, in the end, what works well. And for those that actually know what rich regression is here, it's one of the simplest model in machine learning that we can have. Linear regression is probably the simple one, and rich regression is only with stronger regularization. So not always behind big project and let's say even AI project must be some big model, deep neural networks, etc. Okay. What we found out during developing it was that validation is actually quite crucial point of that, because each day that the measurements were made, somehow there was some measurement bias, and we actually don't know why and how it happened. But we could predict the day when this measurement was done with 100% accuracy, but we could not actually predict or exactly classify what is the ripeness of the fruit. So we found out that we need to be very cautious about how we are validating our results to be able to use ideally different data set from different day on different device, different measurements, or at least actually shift the dates in which we measured in the cross-validation to ensure that we don't have measurements from the same days. So how it actually evolved, we created functional prototype. We have web application that is showing to the people that are taking care about the sorting machines, all the results. This is how, this is how it looks like. So let's start it here. So this is a prototype. As you see that the prototype at this moment is not contactless, but is contactful, because we had too much noise in the data to be able to do it with enough of accuracy. So we stepped into from that requirement to have it without touching. We say, okay, let's do the first prototype with touching the fruit. But for the future use, we need to ensure that we are able to be fast enough, because the requirement is that the measurement cannot take longer than half a second. So at this moment, that's not fast enough, but it's good first step to actually get into production. So lessons learned, if I would summarize it, when you want to predict the shelf life, or actually how the fruit is ripe, you find out that it's very difficult to get at one day apples in the different stages of ripeness, because when they are harvested, they are usually harvested at a similar time. So that's something what you don't realize when you start a project. Okay, I actually need to measure not at the given day, but I need to measure the entire year to be able actually to give all the stages of the ripeness. So that was quite interesting. And as I already mentioned, the interference when you try to do it without touching, so it's so strong from all the devices that are there, from moving parts, etc., that it was very difficult to achieve results that would be satisfactory with this little amount of data. So hopefully we will collect more and we will be able to finalize with the touch lessons. So thank you. That's all from my side.